We forget the quadrilateral bit. If it's a parallelogram, it has to be a quadrilateral, which is a lot. I mean, that doesn't just mean it's four-sided, it also means it's a polygon, right? And that means it's made up of line segments, and that means it's closed, and that means it's a simple figure. There's probably something else in there that I'm forgetting, but it means a lot of stuff, okay? But generally, when we think about parallelogram, the first thing we think about is its opposite sides are parallel. So it's a quadrilateral, and its opposite sides are parallel. Both pairs of opposite sides are parallel. Two pairs. Remember, when it says exactly one pair of sides is parallel, it's talking about a trapezoid, not a parallelogram. So exactly one pair of parallel sides, that's a trapezoid. Two pairs of parallel sides, that's a parallelogram. So that's the first thing we know about every single parallelogram. That's kind of the definition of a parallelogram. And then we proved some stuff, didn't we? That's where you guys say yes. Yeah. Good job. Okay. So we proved some stuff. We proved that in a parallelogram, I don't know, what's something we proved? Okay. The opposite angles are congruent, aren't they? Okay. Let's see. We proved... Ansley, did you say a different one? Oh, is that the same one? Do you know a different one? The opposite sides are congruent in every parallelogram. What's something else we know about parallelograms, Kimball? That is perfect. Something about the diagonals. What's that something about the diagonals we know? Oh yeah, they bisect each other. Okay. Awesome. Okay, they bisect each other. I wasn't even thinking about that one. Let's see. What else do we know about parallelogram? That what? The not corresponding, what's that word? Consecutive, yeah, consecutive. The consecutive angles like this one and this one, those two are supplementary, right? This one and this one are supplementary. This one and this one are supplementary. Was that everything? I think that's 5 things, right? Okay, so all right. So that's all the crap we proved. If we have a quadrilateral where two pairs of sides are parallel, then we can prove all this other stuff. That the opposite angles are congruent, that the consecutive angles are supplementary, that the diagonals bisect each other, and that the opposite sides are congruent. Okay, so today's lesson is the converse day. Remember converse? Yeah? That's where we take the hypothesis and the conclusion, and what do we do with them? We switch them. Okay. So we've been doing this. If it's a parallelogram, okay, so this is parallelogram, then, what's the one I want? Then the opposite sides are congruent. Well, guess what? If it's a quadrilateral and it's a if the opposite sides are congruent, then guess what? It's a parallelogram. So if this is the case, we can prove that the opposite sides are parallel to one another if these sides are congruent. Okay? If it's a quadrilateral and its opposite angles are congruent, then it must be a parallelogram. See, if I know this, can't I prove that the sides are parallel to one another? Think, yeah? Think? Extend that out a little bit. Make that a transversal. What are we looking at right here? Two parallel lines cut by a transversal, and what are these, Logan? What did you say? What's the relationship with these two angles? I don't think that. Yep. Consecutive what? And what do we know about consecutive interior angles? They're supplementary if these two lines are parallel. Now that only proves those two are parallel. It doesn't prove these two are parallel. But look, if you extend those two sides out and you look at this one like it's the transversal, well, look again. Consecutive interior angles are supplementary. So these two lines have to be parallel, don't they? So we can prove that it's a parallelogram. If the diagonals bisect each other, we can prove that these sides are parallel. What do you think about that one? Who says that sounds easy? I almost tricked one of you. What if we say the opposite sides angles are congruent? Could we prove that these sides are parallel? If I gave you a choice between proving this one, where we know the opposite angles are congruent, or this one where the diagonals bisect each other, who would take diagonals bisect each other proof? Who would take this proof? Yeah, good choice. Good choice. Let's look at page 377. The Ride of Terror. You guys see that thing? An amusement park ride has a moving platform affixed to 4 swinging arms. The platform swings back and forth higher and higher until it goes over the top and around in a circular motion. In the diagram below, AD and BC represent 2 of the swinging arms, and DC is parallel to the ground, line L. Explain why the moving platform B is always parallel to the ground. What do you think? If you were on that ride, would you feel like you would stay parallel to the ground all the time? Yost is like, no, you're not getting on that ride. So let's see. All right, so here you are, whee, right? And the ride looks something like this. And it looks like it's got some big giant weights on the end of it over here to counteract all of the weight that we have up on the top, right? And it has our rotation points. Is this thing going to stay a parallelogram? It is, isn't it? As it rotates around. If this side, DC, is parallel to the ground, there's our ground line L. If these two are parallel, and these are fixed, right? These are fixed to the ground. Then no matter how we rotate this thing, it's going to stay a parallelogram, isn't it? And this side is going to stay parallel to that side, which, if everything stays connected, which is always the fear when you get on a ride, right? Yeah. Especially ones with those weird amusement park traveling amusement show things. You guys gone on those? Those are always a little more, I don't know. There's something about loading it up on the back of a truck and hauling it to the next town that makes me a little nervous.
And when you get people that, when it falls off the stable, they're beating the wood plank back under it, that's what's good.
Yeah. And the guy running it doesn't look too stable either. So yeah, get a little nervous. Okay. I don't know. You get it? Carly, did this make sense? Does it seem like, why is Mr. Collard even talking about this? Obviously that's right. Exactly. That's exactly right. Let's look at example 2. Let's see how easy this one can be. I know you guys want to pack. Y, x plus 7, x plus 9, and 2x minus 1. Hold on. This is a good one. Check this out. It's a parallelogram. We know the opposite sides are congruent. So what's the equations we can come up with? Y equals x plus 7 and x plus 9. Dang. I was hoping we'd come up with one you had to use substitution or elimination on. But you were saved right there, weren't you? Because you can find x and then plug it in. But tomorrow when you walk into class, I wonder if it's possible you might get one of these where the other equation says something like x plus 9 equals 2y subtract 1, and you have to use substitution or elimination. Ansley says no. Coria, what do you think the odds of that happening are? Pretty high. See you guys.